Let me start with a simple question. If I told you there's a new technology that can put silver right at the heart of the next generation of batteries, would you think that's an exaggeration? Because this isn't about just another industrial use. This is about the bottleneck that separates prototype from real world. And when a bottleneck breaks, the market doesn't rise nicely. It rises fast. Now take a breath and stay with me, because today I'm going to show you what this technology really is. No jargon, no hype. Why it's different from silver in electronics and silver in solar. The analogy that makes this click in your head in 10 seconds. And most importantly, what needs to happen for this to become large, real, measurable demand for silver, and not just a promise. And at the end, I'll give you 3 practical signals to monitor so you know if this story is becoming reality or staying in the drawer. Before the disclaimer, if you're new here, nice to meet you. Ken AG. Here we separate pretty ideas from functioning industrial chains. Quick disclaimer. This content is for educational and informational purposes only and does not constitute financial investment or trading advice. I'm not recommending the purchase or sale of any asset. The setup. Why batteries matter for silver. You already know silver is both a monetary metal and an industrial metal. But there's a detail many people ignore. The new demand that moves price doesn't come from a small sector. It comes from sectors that scale like a tsunami, have money, and don't accept being without supply. And batteries are exactly that. Because the world is trying to electrify everything. Cars, trucks, data centers, grid storage, industrial backup. Every major economy has committed to electrification targets. China wants full electric vehicle adoption in major cities by 2035. Europe has banned internal combustion engine sales by 2035. The US is pushing massive incentives through the Inflation Reduction Act. This isn't a maybe. This is policy, this is capital, this is infrastructure. And then comes the question, okay, but doesn't that already use silver? It does. But in general, silver goes into contacts, components, solders, electronics. What I'm going to show you today is different. It's silver being used as a functional part that solves a physical bottleneck. And when a material becomes key to reliability, it stops being optional. It becomes critical. Let me explain the difference. Right now, silver is used in batteries as a conductive element. It's in circuit boards. It's in electrical contacts. It's valuable, but it's not structural. You could theoretically substitute copper or other conductors in some applications. You'd lose performance, but you wouldn't lose functionality. But what we're talking about today is different. This is silver as a structural component that prevents catastrophic failure. That's not substitutable. That's critical path. What are solid-state batteries and why they crack? Solid-state batteries are the big dream of the sector. The promise is more density, more range, more safety, potentially faster charging, less fire risk compared to some current systems. Now, let me give you numbers, because promises without numbers are just marketing. Current lithium-ion batteries, the ones in your Tesla, your phone, your laptop, they have energy density around 250 to 300 watt-hours per kilogram. Solid-state batteries promise 400 to 500 watt-hours per kilogram. That's 60 to 80% more energy in the same weight. For an electric vehicle, that means range goes from 300 miles to 500 miles with the same battery pack. For aviation, for drones, for applications where weight matters critically, that's transformative. Safety is another angle. Current lithium-ion uses liquid electrolyte. That liquid is flammable. When batteries fail, when they overheat, you get thermal runaway, fire, explosions. You've seen the videos, Tesla fires, phone fires. Solid state replaces that liquid with a solid ceramic electrolyte. No flammable liquid means much lower fire risk. That's huge for insurance, for regulation, for consumer acceptance. But there's a problem. They crack. More specifically, the internal solid material, the ceramic electrolyte, suffers from cracks and failures. And a crack in a battery isn't an aesthetic defect. A crack is the beginning of the end, because a crack opens the path to instability, short circuits, degradation, performance loss. The battery doesn't just lose capacity, it fails catastrophically. Let me explain why cracking happens. When you charge and discharge a battery, the materials expand and contract. Lithium ions move in and out of the anode and cathode. That movement creates stress. In liquid electrolyte batteries, the liquid can flex, can accommodate that stress. But in solid state, the ceramic electrolyte is rigid. It can't flex. So stress builds up. And when stress exceeds the material's fracture toughness, it cracks. This is a fundamental material science problem. Now comes the interesting part. Researchers have shown that an ultrathin layer of silver, applied in a specific way, can reinforce that ceramic electrolyte and reduce the chance of cracks. It's as if silver becomes an invisible stitch in the microstructure. And this is the kind of solution that changes the game. How does it work mechanically? Silver is ductile. It can deform without breaking. When you apply an ultra-thin layer of silver at the interfaces or within the ceramic matrix, it acts as a stress buffer. When the ceramic wants to crack, the silver deforms slightly and absorbs the stress. It's like adding reinforcing fibers to concrete. The concrete is brittle, but add steel rebar and suddenly it can handle tension. Silver is the rebar for ceramic electrolytes. But hold on, this doesn't yet mean gigantic demand tomorrow. It means there's a plausible technical route. What's missing is transforming plausible into industrial, and that's the gap that kills most breakthrough technologies. The valley between lab and factory, the place where 95% of amazing science dies. The bridge analogy. This makes it click. Think of a bridge, a giant steel bridge. You can have the best design in the world, the best pillars, the best cables, but if there's a weak point, a joint that cracks with vibration, heat, time, the entire bridge becomes a gamble. Now imagine someone discovers a material that applied in a super thin layer on that fragile joint makes the bridge withstand twice as much without changing the rest of the design. The cost isn't the material being expensive. The cost is the bridge falling. Battery is the same thing. An electric car can't be maybe. A data center can't be let's see. And that's why if silver becomes that layer that prevents the crack, it can move from the dispersed use category to the structural use category. And structural use is where demand gets serious. Let me give you a comparison. Silver in solar panels is dispersed. Each panel uses about 20 grams. It's significant in aggregate. Millions of panels mean hundreds of millions of ounces annually. But it's not structural. If silver price spikes, manufacturers can reduce silver content, use alternative pastes, redesign cells. They do this constantly. Silver content per panel has been declining for years, even as total panels produced increases. Let me give you specific numbers so you understand the scale. In 2020, solar panels consumed roughly 100 million ounces of silver. By 2024, that grew to about 130 million ounces, despite silver content per panel dropping from around 20 grams to 15 grams on average. So volume growth overcame content reduction. But the key point is that content reduction is possible. It's elastic. Manufacturers optimize constantly. Electronics is similar. Smartphones, laptops, servers, all use silver in contacts and circuit boards. Total electronics demand is around 250 million ounces annually, but it's distributed across billions of devices. A phone uses about a quarter of a gram, a laptop maybe half a gram. So even if silver spikes to $200, the impact per device is minimal, 25 cents in a $1,000 phone. Manufacturers absorb it or substitute where possible, but structural use is different. Assume they capture 20% of the premium EV market by 2030. That's roughly 4 million vehicles annually. If each battery uses 10 grams of silver for the electrolyte reinforcement layer, that's 40 million ounces per year from EVs alone. Add grid storage, aerospace, defense, consumer electronics, and you could be looking at 60 to 80 million ounces of new structural demand. That's comparable to solar, but unlike solar, it would be growing from zero. Solar took 20 years to reach 100 million ounces. If batteries scale faster, if adoption is concentrated in 5 to 10 years, the demand shock is much more acute. That's the difference between gradual supply adjustment and a scramble. Killing 3 illusions before you get hyped. Let's kill 3 illusions now so you don't fall for easy narrative. 1, this doesn't mean every battery will use silver. It could become a niche. It could become a premium line. It could stay just a research stage. Most battery innovations never scale. Lithium sulfur, lithium air, aluminum ion, sodium ion, all promised breakthroughs. Some might eventually work. Most won't reach commercial scale. 2, this doesn't mean silver will rise because of this alone. Price is a system. Macro, dollar, rates, flow, derivatives. One application doesn't control price. Solar is massive for silver, over 100 million ounces per year. But solar didn't make silver go to $100. The macro environment did. So even if solid-state batteries scale, even if they use silver, the price response depends on overall market conditions. 3, this doesn't mean the technology is already ready. Science isn't a factory. There's a difference between proving something works in a lab and producing it at scale profitably. The lab has PhDs controlling every variable. The factory has line workers running 3 shifts trying to hit throughput targets. Those are different worlds. So the game here is what needs to happen for this to cross the desert between laboratory and production. And this is where most videos fail because they stay in the wow. We're going to stay in the okay, so prove it. The 6 steps from lab to real demand. I'll give you this in 6 steps. And if one step fails, demand becomes smoke. Step 1, repeatability at scale. It's not enough to work once in the laboratory. It has to work with different batches, with different suppliers, with temperature variation, with repeated cycles, and with acceptable defect rate. Industry only buys solutions that handle variability. Let me explain why this matters. In the lab, you control everything. You use high purity materials. You control temperature to 1/10 of a degree. You monitor every step. But in production, you're using materials from multiple suppliers. Your equipment isn't perfect. Your environment fluctuates. Workers make mistakes. The process has to be robust enough to handle all that variability and still produce good product. Signal that this is happening, validation articles by independent groups, plus tests with larger cells. If you see research from 3 different universities, 2 different companies, all showing similar results, that's validation. If you see tests moving from coin cells, which are tiny lab-scale batteries, to pouch cells or prismatic cells, which are commercial formats, that's scale up. Step 2, production line compatibility. Factory is a religion called throughput. If applying this silver requires a slow, delicate, expensive process that slows down the line, it dies here. The point is, the layer is ultrathin. That helps. But it needs to be applicable quickly, applicable with industrial equipment, with high yield, with simple quality control. Current battery manufacturing runs at enormous scale. A single gigafactory produces millions of cells per year. That means cells per minute coming off the line. Any process step that slows that down costs money, millions of dollars. So the silver application has to be fast. It has to be compatible with existing equipment or require minimal new equipment. And it has to have high yield, meaning most cells pass quality control. Signal, patents and partnerships with materials companies, electrolyte manufacturers, or deposition equipment makers. When you see patent filings for manufacturing processes, not just the material itself, that means someone is thinking about production. When you see partnerships announced between a battery company and a material supplier, that means they're building a supply chain. Step 3, aggressive cycling, real lifespan. A commercial battery has to survive hundreds, thousands of cycles. Vibration, heat, fast charging, abuse because users aren't careful. If silver solves cracks at the beginning but then creates another problem, the industry abandons it. Let me be specific about what commercial requirements look like. An electric vehicle battery needs to survive 1,500 to 3,000 charge-discharge cycles, while retaining at least 70 to 80% of original capacity. That's 8 to 15 years of driving. Grid storage batteries need to survive 10,000 to 15,000 cycles. That's 20 to 30 years. These are brutal requirements. The battery has to work in Arizona heat and Minnesota cold. It has to handle fast charging that stresses the materials. It has to survive being discharged to near zero, then recharged, over and over. Signal published results with long lifespan and stability under severe conditions. If you start seeing papers that show 2,000 cycles with minimal degradation, that's promising. If you see tests at extreme temperatures, -20 to +60 Celsius, and the battery still works, that's commercial grade. Step 4, economics, cost per kilowatt hour and cost of risk. This is where the market becomes adult. The question isn't, how much does silver cost? The question is, how much does it cost not to use it? If the silver layer increases reliability and reduces recalls, warranties, fires, reputation damage, the CFO approves. But it needs to make financial sense. Let's do math. A typical electric vehicle battery pack is 60 to 100 kilowatt hours. Current cost is around $100 to $150 per kilowatt hour. So a 70 kilowatt hour pack costs $7,000 to $10,000. Now, if adding a thin silver layer costs an extra $50 to $100 per pack, that's 1% of total cost. But if it reduces failure rate from 1% to 0.1%, if it extends warranty life, if it prevents fires that cost millions in recalls and reputation damage, that $50 to $100 is worth it. Signal, manufacturers publicly talking about failure reduction, yield increase, safety improvement. When a company announces we improved our battery safety rating or we reduced our warranty claims, that means they implemented something that works. And if silver is part of that, demand follows. Step 5, adoption by at least one major player. Industry works by domino effect. If a major player adopts and shows performance, the others rush to follow. Because nobody wants to be stuck with inferior technology. This is how every battery chemistry is scaled. Lithium-ion wasn't adopted by everyone at once. Panasonic and Sony started. Tesla partnered with Panasonic. Others saw the performance and followed. Now lithium-ion is the standard. Let me give you historical context because battery technology adoption follows predictable patterns. Nickel metal hydride dominated hybrid vehicles in the 2000s. Toyota Prius made it the standard. But when lithium-ion showed better energy density and lighter weight, the entire industry shifted within 5 years. By 2015, nickel metal hydride was legacy technology. The transition wasn't gradual, it was abrupt. Have you ever wondered what the future of energy storage looks like? We talk a lot about lithium-ion batteries powering everything from our phones to our cars, but what if I told you there's a new player in town, one that could completely revolutionize the game? I'm talking about solid-state batteries. And what's even more fascinating, is how this new technology could shake up a market we've known for centuries, the silver market. Stick around, because today we're diving deep into the electrifying world of solid-state batteries and their surprising connection to one of the world's most precious metals. First, let's get the basics down. What exactly is a solid-state battery? Think of your current lithium-ion battery. It has two electrodes, an anode and a cathode, and a liquid electrolyte in between that allows charged particles, or ions, to move back and forth, creating electricity. Now, the key word there is liquid. That liquid electrolyte is often flammable, which is why you sometimes hear about batteries overheating or catching fire. Solid-state batteries, as the name suggests, replace that liquid electrolyte with a solid material. This could be a ceramic, a polymer, or glass. This simple change has massive implications. By getting rid of the flammable liquid, solid-state batteries are inherently much safer. The risk of thermal runaway, that chain reaction that leads to fires, is practically eliminated. But safety is just the beginning. This solid structure allows for a more compact and energy-dense design. Imagine an electric car that could travel over 1,000 kilometers on a single charge, or a smartphone that lasts for days, not hours. That's the promise of solid-state technology. They can also charge much faster. We're talking about charging an EV from 0 to 80% in just 10 to 15 minutes. This isn't just an incremental improvement. It's a quantum leap forward. So where does silver fit into all of this? This is where it gets really interesting. While lithium is still the star of the show, a key component in many promising solid-state battery designs is a material called silver-doped argyrodite. That's a mouthful, I know. Argyrodites are a class of solid electrolytes known for their excellent ionic conductivity, meaning they're great at moving those lithium ions around. And scientists have found that adding a small amount of silver to these materials can significantly boost their performance and stability. The silver acts as a sort of superhighway for the ions, making the battery more efficient and reliable. It helps to prevent the formation of something called lithium dendrites. These are tiny, needle-like growths that can form inside a battery over time, eventually causing it to short-circuit and fail. By incorporating silver, researchers are creating a more robust and long-lasting battery. It's a fascinating example of how an ancient precious metal is finding a new, high-tech purpose in the 21st century. Now, let's talk numbers and market impact. The global demand for silver is already massive. It's used in jewelry, silverware, coins, and of course, a huge range of industrial applications. Think solar panels, electronics, and medical equipment. In fact, industrial use already accounts for more than half of all silver consumption annually. The photovoltaic industry, for making solar panels, is a particularly huge consumer. So the silver market is already running on a tight supply-demand balance. Now let's layer on the potential demand from solid-state batteries. The electric vehicle market is projected to grow exponentially in the coming decades. If even a fraction of those future EVs are powered by solid-state batteries that use silver, the demand could skyrocket. We're not just talking about a small bump. Some analysts predict that the battery sector could become one of the largest consumers of silver, potentially rivaling the demand from the solar industry. Let's break it down. An average EV battery today contains a significant amount of materials, but imagine adding a new key ingredient, silver. While the exact amount of silver per battery is still being optimized by companies like Samsung, Toyota, and QuantumScape, even a small quantity, when multiplied by millions of vehicles, creates a massive new source of demand. Some estimates suggest that the amount of silver needed could be anywhere from 20 to 100 grams per vehicle. If we hit the high end of that estimate, and we produce 20 million EVs with these batteries, that's 2,000 metric tons of silver per year, just for this one application. That's a huge number when you consider the total annual silver mine production is around 25,000 metric tons. This presents a classic economic scenario, a massive surge in demand for a resource with a relatively fixed supply. Silver mining isn't something you can just ramp up overnight. It takes years to explore, permit, and build a new mine. So what happens when a new powerful source of demand enters a market that's already in a deficit? The price tends to go up. Many market experts are already pointing to silver as one of the most undervalued assets, even before factoring in this new demand driver. The silver squeeze from solid-state batteries could be the catalyst that sends its value to new heights. So who are the major players pushing this technology forward? You've got automotive giants like Toyota, which holds over 1,000 patents related to solid-state batteries and plans to commercialize them in the next few years. There's also Volkswagen, which has invested heavily in QuantumScape, a startup out of Stanford University that's a leader in the field. And then there are the tech behemoths like Samsung and LG, who are pouring billions into research and development. This isn't some fringe science experiment. It's a full-blown race between some of the world's biggest corporations to unlock the holy grail of energy storage. The timeline for widespread adoption is the big question. While we're already seeing prototypes and pilot programs, mass production is a complex engineering challenge. Most experts believe we could all start to see the first EVs with solid-state batteries hit the market in the mid to late 2020s. From there, as manufacturing scales up and costs come down, adoption could accelerate rapidly. This means the impact on the silver market isn't necessarily an if, but a when. The market is forward-looking, so we could start to see the price of silver react long before these batteries are in every car on the road. This creates a potentially huge opportunity for investors. As the world transitions to cleaner energy and more advanced technology, the demand for critical materials like silver is set to grow. Unlike other commodities, silver has this unique dual identity. It's both an industrial metal, essential for our technological future, and a precious metal, a store of value that people turn to during times of economic uncertainty. This combination makes it a particularly compelling asset. Of course, no investment is without risk, and technology can evolve. Researchers are exploring other materials for solid electrolytes that don't use silver. However, right now, silver-based compounds are among the most promising and well-researched options, giving them a significant head start. The sheer amount of investment and patent activity centered around silver-doped argyrodites suggests that this is the path many industry leaders are betting on. So, to sum it all up, we're on the cusp of a battery revolution with solid-state technology. These batteries promise to be safer, more powerful, and faster charging than anything we have today. A key ingredient in making this revolution happen could be silver, a metal we've valued for thousands of years. This new, potentially massive source of demand is entering a market where supply is already tight, creating the perfect storm for a significant price appreciation. From powering our future electric cars to underpinning a new wave of technological innovation, the future for silver looks incredibly bright. It's a fascinating story of old world value meeting new world technology. What do you think? Is silver the secret ingredient to our energy future? Let me know your thoughts in the comments below. And if you enjoyed this deep dive and want to learn more about the technologies and markets shaping our world, make sure to hit that like button and subscribe for more content, just like this. Thanks for watching, and I'll see you in the next video.